Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. Last week we started with a general introduction really about the history of information retrieval. We namely Boolean retrieval, so true and false, which as computer science students should have no secrets for you, but we'll see how we can actually turn this into an information retrieval system. And on top of this, it's going to be a system that you will be able to implement as part of the exercise next week. So you will actually have your first information retrieval system Boolean based. Now, what did we see? We saw that data has shapes, and this is in fact a database lecture. We saw that the first shape is tables, relational tables with rows and columns. We saw that there is a second shape called trees, which corresponds to denormalized data, as we will see in big data maybe next year if you join. Then we have, don't strike again, very slow, graphs, which have nodes and edges, but unlike trees, you know that graphs can actually have cycles. So you might know Neo4j, for example. Data cubes are a bit like tables, except that they can have extra dimensions. So you can slice, dice, and so on. It's very popular for business people, for sales data, for example, balance sheets, income statements. And finally, we have unstructured text, which maybe was considered by the general public to be a bit boring or more boring than the structured data. But first, with web search 20 to 30 years ago, and plus now all the large language models, I think that this is suddenly catching a lot of people's attention right now. And this is the focus of information retrieval. So information retrieval is about looking for information in collections of unstructured data, right? You have an information need. I'll talk more about this. This is what you're looking for. And you're looking for information in a large collection. Note that the definition of information retrieval does not exclude the more modern large language models, because you could argue that ChatGPT is also doing that, right? So this is a very broad definition of information retrieval. So I have a question that I'd like to ask you to check if you've been following last week. I'd like to do this at the start of every lecture, and then we will go ahead with the material of this week's lecture. So why don't you grab your smartphones or laptops and go to the usual address, same as last week, and answer the following question. What is the Dewey Decimal Classification? So we have four answers. Answer A is that it's the core algorithm used by Google to index the web. Answer number two, it's a number-based system used by many libraries in the world to sort and retrieve their books. Or is it a standard used by mathematicians to classify sets? And QRC, this classification is also paramount to information retrieval, as documents are encoded as numbers. Or query Dewey and decimal \5 classification, pipeline curl /post app1.tlg.ch. You can participate in the lecture room, but also online. We have a majority here. We obviously also have people that already built an information retrieval system to answer my questions. But this answer is in fact correct. Remember that this is the system that is used with these 3 digits and a decimal period and other digits in order to classify books by topic. In fact, now that I know that most of you take the machine learning lecture, who heard about clustering? So the Dewey Decimal Classification is basically a clustering system that was invented before machine learning, because this is all about this. You try to group the books that belong together and that have topics that are similar. Okay? Oh, let me get back to the slides. Right now, I'm just crossing my fingers that, oh no, not the right one, click too fast. This one, I prepared everything correctly, and I'm supposed to land back exactly to the right place every time. There you go. So let's start with a naive approach. Imagine that you have what we call a corpus, which is text, large quantities of text. Here, all of Sherlock Holmes, it just fits on your laptop. So you could think of using that, like you download it from the web, just a simple search gives it to you because it's public domain, actually. This is the reason why now it's so easy to find all the everything that Arthur Conan Doyle wrote. And every year there's actually new ones, makes it very exciting for the information retrieval courses. So imagine that you have this on your computer. It's a few megabytes of data, and you want to search for words in there. What would you spontaneously do as a computer scientist? You have a specific term, you want to find where it is in the documents. You have a command line window. Starts with a G. Yes? Grep, exactly. That would be a first good idea, right? You could use Grep and you could try to find the words in the document. So let's try to do this, right? Imagine that I have everything, even 3 megabytes. And I want to, this is my query. I want to find all the lines in that document that have the word lawyer. So I can do it with Grep, indeed. I can just, so this is an example of line that I would like to find. And indeed, I can use the command line with Grep, Grep lawyer, the word I am searching for, and then corpus.txt, which has the entire text. And what's amazing is that it's actually, runs on your machine. And you see, this is, I actually did it. You see on every line, you will see that, that there is the word lawyer. This is what Grep is doing, right? So for example, right here, 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 and so on, right? So you will find on every single line the word lawyer. So that kind of does the job, right? You can actually use Grep and you can find all of the lines that contain that word. Why lines? Just because this is the way Grep works, right? Grep is basically organized looking at the return, carriage return, and then it does it line by line. Now, something more complicated. Imagine that now you want to find 2 words. Can you still do it with Grep? How would you do it with Grep? On the same line, you want to have these 2 words. Yes, exactly, another Grep with a pipe. It's actually not a bad thing that it's slow because it slows me down and you have more time for understanding. So you pipe it through another Grep command, exactly. So this is what you get. And now there's only 2 lines that are actually left from the entire corpus, and these are these 2 lines, right? So you can implement an AND. An OR, this is where it starts being more complicated, right? You can also implement NOT because you have this magic parameter of grep-v that is reverting the whole thing and actually looking for the lines that do not have the word silver. And this one is the only surviving line. You see, it has Penang, it has lawyer, it does not have silver. So we know how to implement AND and NOT. Now you could think, okay, how do I implement OR? How do I implement more complex queries? But I would like to ask you this. Which of the following is the shortcoming of Grep? Basically, it has limits, right? You cannot just use this and then be done. Otherwise, the course is over and goodbye and see you at the exam, right? So first, it cannot rank results. Second, it sometimes returns documents that do not contain the term being looked up. It does not, there's a typo, that's annoying, the ED. It does not have proximity semantics, or it cannot scale up so easily. Probably set it up to multiple answers possible. Let's look what you say. So you all agree on the first, third, and fourth answer. And the reason you disagree with the second one is probably not just because of the typo. It's actually not true. It's really a question we will see later about false positives, right? But with grep, there are no false positives, right? Just looks at the lines and either it contains the word or it doesn't. So indeed, that cannot happen. But it's true, it cannot rank results. It's just returning the lines in the order of the document. It does not have proximity semantics, like is a word close to another word other than on the same line. And it cannot scale up so easily because, as you can imagine, you cannot grep the web. Right? You can grep something you downloaded to your laptop, but that's pretty much it. And even on your laptop, if you download a gigabyte of data and run a grep on it, it's not going to return as instantly as a web search engine. So there are limitations to grep. And so that's not actually it, right? We need something better than grep for the use case that we have. I'm not saying that grep is not a good tool, right? I'm just saying for the use case that we have right here, information retrieval, grep is not what we are looking for. Note that grep has regular expressions. So it is powerful. You could imagine that you could implement something like an or more complex queries, even wildcards, as we will see. So it does have a few nice features. You remember regular expressions, right? From the theoretical computer science, right? It's the simplest kind of grammars that you can have. They correspond to a deterministic automaton and regular languages. All right. But we do have shortcomings. First, it doesn't scale up because you cannot apply it to the full web, or you would still be here in a couple of centuries trying to do this. In fact, there is this excerpt from a book that kind of was telling how things happened when in the very early years of Google. It is like, to do it right, in old page, you'd really have to capture a significant chunk of the World Wide Web's link structure. Page said, sure, he'd go and download the web and get the structure. He figured it would take a week or something. And of course, he later recalled it took like, yeah. But they did it. They did manage to download the web and even build the structure and see what it looks like on top of it, right? But it's not trivial. You cannot just snap your fingers and that's it. You have downloaded the web and you grep it. Proximity search would correspond to queries that look like this, where you could have a keyword near that says that must be near Switzerland. You do have a possibility, I think, on grep of showing the lines, the 5 lines before, the 5 lines after. For example, I think it's dash uppercase A, dash uppercase B. So you do have ways of maybe coming up with something that does kind of emulates it, but it would be a bit complicated, right? Not out of the box. And next, how do you rank? Because if you type a search in web search, you do not get the results in any order, right? Because there are billions of pages that might be talking of the legendary Röstigraben, but you want the most relevant ones. So there has to be a way of sorting these pages, right? And we would like something from something like this from an information retrieval system. In fact, we will build systems that are able to rank in a few weeks, not just quite yet. For now, we are not going to try to rank, but this will come, and this is an important feature of an information retrieval system, especially when there's a lot of data. You see here, there are 72,800 results, right? And you cannot possibly, as a human, go through all of them, so you do need a bit of help with the sorting. Okay. Now, there is a trick that we are going to use in order to be faster than Grep and more efficient and also specific to our use case. That is called an index. That's called an index. You already heard of indices, probably in the context of relational database systems. Who already heard of an index? Who never heard of an index? But you did hear about the indices at the end of a book, right? You take a book and look at the last pages. You do have an alphabetical list like this, where you have links to pages, right? And this actually is the idea. We need to do, it's yet another example of something that existed before computers that was enabling us to find information faster. This is the way to go. This is the idea. It's alphabetically sorted list of words. And then you can look at the page and go directly to the page. Okay. So this is the idea. But before we do that, I'm a database researcher, so I like to model things. In fact, it's something that you should do pretty much everywhere. A model is basically some sort of abstraction from the world. The world is very complex, very complicated. And so you need to look at the world through special abstraction lenses that simplify a few things. But the thing you simplify, that depends on what you are doing. You would not simplify things in the same way for different same way than a database researcher or a chemist, for example. So we need to model things. And first thing that we are going to do in the context of unstructured text, we are going to come up with a model for what we are processing. And it is based on that model that we will be able to build our system. So it will be a bit of a simplification. The first concepts that I have in my model, I need to say what we are going to be talking about. The first concept that we have is the concept of a document, right? It's an abstract concept. In a library, you could think of a document as a book. One book is one document. In the context of the web, you could think of it as a web page, right? But of course, it depends on the context, right? You could also imagine that you have videos or any other kinds of items, right? So we have this abstraction of a document. It's not as trivial as it seems to say what is a document and what is the granularity. I'm going to come back to that next week, but we'll assume that we have that. We have this notion of document. So that would be, for example, I think that's from the ETH library, that pretty much any information system like this, you type something and it returns documents. This could be books. Okay. That's the first concept. The second concept that we are going to need is the concept of term, a term. Today, we are going to keep it simple and consider that a term is basically a word. Right? So Sherlock is a term, lawyer is a term, Switzerland is a term. Sometimes, and we will see the complexity of that next week, you could also consider that several words together as a term. So Unterwalden liegt dem Wald, which is the actual name of the canton, Uwe. ETH Zurich would be considered also a single term, person, watch, run, paper, book, and so on. So we have terms, we have documents, and we have terms. And then the link between the two is fundamental because we have a relationship between the terms and the documents based on which we are going to build our system. So this is an example of a document. I'm not going to sing because it's not December 6th, but this is an example in Swiss German. You don't need, I assume most of you understand Swiss German, but you don't need to understand it to get the point of what I'm going to say. This is by Mani Matter for those of you who recognize. So we have this document D, and then we can say that a term, for example, Hölzli, can be included in a document, right? I could write it like this, like Hölzli as a string, that's a term, belongs, and here I'm using the mathematical notation, belongs to the document D, right? So it's a set membership, right? So in that case, you already probably imagine in your mind, the document is a set of terms, right? If a term can belong or not belong to a document. So that's first abstraction coming here. That's one thing that you could say. But you could also be interested in the number of times that a term appears in a document. Because if you look closer, now you see that Huxley appears twice in these documents, right? Retrieval from Huxley there, that's Huxley default. Twice. So maybe you want to include in your abstraction also that the number of times it appears, which I just used some arbitrary notation, Huxley appears twice in documents. But you notice that there is more information in there. Because if you look at the former slide here, this is not captured. Set membership doesn't capture any number of occurrences. So this is something more powerful. In fact, there is a name for that. We commonly call it a bag rather than a set, when you also have the number of times that a term can occur in a document. What else could you be interested in? Yes. Where in the document the term is? Absolutely. This is also something that in some systems we are interested in. So for the purpose of the abstraction, I'm going to slightly reformulate where exactly it appears as the order in which the terms appear, which is slightly equivalent. But you are right that the location at which it appears, we will see that we can actually include that in the structures that we are going to build. For the purpose of the abstraction, this is really about your remark about the order in which the terms appear in the document. So for example, in that case, Flamme happens before Pure in the document, right? So the three things that we might be interested in between a document and a term is inclusion, whether or not a term appears in a document. Second, the occurrence, the number of times that it appears in a document. And third, the order in which it appears in the document. Note that if I have all three of them, I have all of this information here, I can actually reconstruct the document. I know exactly how many times, the number, the order in which they appear. I do have the original document, so I didn't actually lose any information. Right? What if I don't want to keep the order? I don't care about the order. So you understand here that we drop information. We forget about the order, so now I don't care about it anymore. And now I'm not able anymore to read the book, right? So of course, that's probably less interesting to read a Dan Brown book as a bag of words than as a list of words, but for indexing purposes, that actually be helpful, right? So this is what we get. We still have the number of occurrences, because if you actually look a bit closer in there, you will find a few terms that are multiple times in there. Let's see if I copied correctly. Yes, exactly. I think I really tried to delete correctly this. So you see, you do have the number of occurrences in there. So this is then a bag. And you can drop also the number of occurrences, and then you're back to a set, just the inclusion. And now you see we forgot the number of times that the terms appear. This is just once, and that's it. It's a yes or no. So you see, list of terms, bag of terms, set of terms. This is not even new to here, because if you visited the database management lecture, relational databases, you probably also remember that a table can be seen as a set of records, as a bag of records, or as a list of records. Right? You can actually say the same thing. So it's not really a coincidence that you can have these three structures. Right? Okay, so this is the abstraction that we have. Now, today, we are going to take this. We are going to reason on the sets. But depending on the week, we might change. In some weeks, we are going to be interested in lists of words. In some other weeks, in bags of words. But I will tell you every time what we assume. Right? For today, we are assuming that the document is a set of terms. By the way, you probably noticed that I used how do I formulate this without ambiguity? So, okay, let me say it with the ambiguity. I interchangeably used the terms word and term, right? For today, you can consider that it's the same. A term is a word. In the coming weeks, I will clarify what we mean. There's a couple of concepts, so I'm going to throw them at you, like term, token, positional token, posting, type, and so on and so on. So these terms have a very specific meaning, and I'll come to that. But again, today we keep things simple. So a term is a word, and that really keeps things simple. All right. So this is our model. This is the data model. We have documents, we have terms, and a term can or cannot belong to a specific document, because today I'm interested in sets of terms. Now the next question is, how do we represent that? Because this is a mathematical abstraction, but now it needs to go into a computer program. So the first idea of how you represent this, the fact that documents contain or not terms, is as some sort of 1 or 0. It's some sort of matrix, right? You have 2 dimensions. You have a first dimension that are the documents, second dimension when you have the terms. And for every value of I and j, if you consider that I is a term and j is a document, then that matrix contains ij is a 1 if document j contains term I, and it's a 0 if document j does not contain term I. And what you get looks like this. It's a matrix, an incidence matrix. And in that case, you have on the rows the terms, and on the columns, the documents. So I just used in the former slide the convention that typically you use in the linear algebra, right? That the first index is the rows and the second index is the columns. It's arbitrary, but if you consider the more general tensors, but this is the convention I use, right? So terms on the rows and documents in the columns. Now I kept things a bit abstract in the sense that for the terms, I just called them, T, U, V, W, X, Y. So I gave them letters. Of course, in fact, that would be more like computer information, retrieval, page, and so on, right? But I just abstracted slightly to think of the terms as letters. As for the documents, I used numbers. This, in fact, is done in practice. We do assign numbers to the documents. This is called a document ID. Right? So a given book is going to have ID 1, another book is going to have ID 2, and so on and so on. So I have document ID. So this is an incident matrix. It's really just a matrix with Boolean values, 2 dimensionals with the terms on the rows and the documents on the columns. Who agrees that this is an appropriate representation of documents as sets of terms? Okay, we have a majority. Who agrees that, or let me formulate it like this. If I give you documents as sets of terms, who of you can give me the matrix? Right? If I give you documents as sets of terms, you should be able to build the matrix. Not the other way around. If I give you the matrix, who of you can reconstruct the sets? Okay, very good. So if you want to reconstruct the sets, if you actually look closer, imagine that you want the set corresponding to a specific document. You look here, 6. You look for all the ones, and then it has U, it has V, and that's it, right? So you can reconstruct the sets. So you see it goes both ways. It's actually a bijection between sets of the collection of sets of words and matrices of Booleans, right? So mathematically, it's very adequate to represent what we are looking for, right? So it's very, it looks good, and we can work on that. So an example, for example, for a Boolean y5, so we have a 1 because term y appears in document number 5. So this means that we are, the mathematical notation we could use is Boolean to the power of terms times documents, aka a function that associates every term and every document to a Boolean. Now I have a question for you. Check that you are really comfortable with this. Imagine that I give you this incidence matrix, which you can understand as a collection of sets of words, a collection of documents. And I'm giving you a query. Somebody is looking for term Y. What does that return? Does it return 1, 2, 3, 4, 6, 7, 9, or maybe 5, 8, 10, or nothing, or all documents? Who bets that everybody gets that one right? Let's see. %93. There you go. Yep, indeed. You can see, I cannot show it because it doesn't project this, but you can basically see, we're in the lecture hall, that Y has a 1 here with document 5, 1 here with document 8, and a 1 here with document 10. Now, what does that tell us, right? So it's easy to do, right? What that tells us is that we had the original collection of books that might be on the shelves in the library. We abstracted away as documents being sets of words and built that matrix. And now if somebody arrives to the library and says, I'm looking for books that contain term Y, then the librarian can answer that query without looking at the books. Just that structure is enough to find the books that we are looking for. This is the one first little success in here. We managed to forget about the books themselves, and we have some structure somewhere that has enough information in there to answer queries like this, where we are looking for terms. Right? So this is the first step towards building our system. So if I now relate this to Grep, what it means is that in the case of Grep, you had to go through the original document that had all the number of occurrences and the order, because this was the original text about Sherlock Holmes by Sir Arthur Conan Doyle. And now we did something that wasn't a grep, it was more like a matrix lookup on less information, because that time we didn't have the order and we didn't have the number of occurrences. So this is the lesson here. We managed to drop information and we can answer queries. Where am I? 3, 4? No, I'm not sure. Did I already do the 3? Sure. Because if I skip an entire couple of slides, I cannot come back on that. Yes, that was the 3 is so if I have a query like this, I can actually look it up, just looking at the corresponding row, find the ones, and that tells me the documents that contain it. In that case, that would be documents 3, 5, 6, 7, 8, and that's it, right? So I can use in this way, right? Just the ones give me the documents. Who can now implement any query that contains one term to look up? Who can do it? What about this? Who is able, with the incidence matrix, to answer this query? Not you. I want all hands raised here, right? So you agree you're looking for the zeros now, right? You just look up the term as well. Then you look for the zeros, and then you have the documents that do not contain the term. React. Yes. You see? Or another way to look at it is that you take the row as a vector of Booleans, and then you do a bitwise NOT on the Booleans, and then you you swap the zeros and ones, and now you have not U. Okay. And that gives you the documents that you are looking for. What about AND? Who is able to answer that query? So most of you, how do you do it? Anybody? We have the catch box here. You can try to use it. Who wants to tell us how you do the AND? Yes, go ahead.
We can use both rows and then just use the AND function to AND each entry bitwise.
Yes, absolutely. So you take the two vectors of the rows, and then you do a bitwise AND, and you keep whenever you have a one for both terms on a given document. For example, that's it. That's the two vectors of Boolean. So these are row vectors. And then you do a bitwise AND as you suggest, like this, and then we get documents 5 and 8, right? So you see it's a bitwise AND. If you look at what's going on here, the one here is lost because there's a 0. This one goes through, this one is lost, this one is lost, this one goes through, and this one is lost because of the 0, right? So this is an AND. So it does the job for AND. What about OR? Who can do it? More hands, who can do it? Right? It's the same, right? You just look at this, you take the two row vectors, you use the OR, a bitwise OR, and then you return the results, right? Like this. So we have AND, we have OR, we have NOT, and we have a simplified incidence matrix that encodes the terms that belongs to which term belongs to which documents. Now, I have another question for you. Which one of the following queries returns documents 5 and 8? So you have U or Y, you have U or not Y, you have U and Y, and you have U and not Y.
Regarding
documents 5 and 8.
There was a question on Zoom.
Yes?
Someone wrote the initial X row has a different X row. The initial incidence matrix. That's different.
Oh, did I change? It might be that I didn't copy it in exactly the same way. You mean on the slides, on the PowerPoint slides? Yeah, maybe I'll fix it. It's not that it's important for understanding, but it's true that it's better if it consistent. I'll look again. I might have not copied it exactly the same way. 5 and 8. Basically, need to use U and Y, and with any combination of and, or, and not, you want to find something that returns documents 5 and 8. Sure. You say 100%, I love that. Okay, now everybody is on board. Okay, and that's the correct answer. I didn't really hesitate. Yeah. So you see, indeed, you have the, if you look at the U and the Y, you have indeed the one right here, and the one, and then the other one right there, and the one. That's pretty much all you have. And the last one disappears because there's a 0 over there. Okay. So now I know that you're following and that everybody is following. So we have a first system that does the job. It's a mathematical system, right? I haven't yet implemented that in a computer, but it is a mathematical system that returns the documents that satisfy a given query. Now, I would like to say a few words about the effectiveness of an information retrieval system, whether it does the job or not. And here there is a subtlety, because if I ask you, basically, are the answers of the system correct? You're going to answer, yes, they are correct. Why? Because this is math. This is just a mathematical truth, right? You return the query, you compute your bitwise and or not, and so on. The math will return the correct documents. So how can we dare question the truth of mathematics, right? It's because in real life, we do not actually just look at the query, we look at what the actual human being is looking for. So imagine that Alice here is looking for her semester's thesis about the impact of global warming on the development of butterfly ecosystems in the southern part of the canton of Uri between 2011 and 2013. Actually, that might be even a PhD thesis. So you might think of different queries, right? Butterfly and climate and Uri and south, or Lepidoptera and UR, the abbreviation of the canton of Uri and not winter, or central near Switzerland or Sweden, you never know. Somebody might have confused it. And not LU or Nidwald or Obwald or Stockholm and, well, for example. So what you see here is that there is not an exact match or an exact correspondence between whatever is going on here and the actual query that you type into the system. The mathematical truth will hold for the queries themselves. Then it's true. There is absolutely no ambiguity. But this is not the question. The question is, whatever answers that Alice is receiving from the information retrieval system with the incidence matrix, does it fulfill the information need that she had in the first place? And that might not be exactly 100%. So we need ways to actually evaluate that. Now, to introduce a bit of terminology, the term for this is relevance. We are asking, is a document returned with these queries relevant or not relevant to Alice? And the only person who can tell is Alice, whether that document is or not relevant to her. All right, so this is why we have to basically analyze the effectiveness of the system. And how we do that, I will tell you after the break. We have 15 minutes, it's 11, and I'll see you at 15 past 11, and I'll tell you how we can actually analyze the effectiveness of the system. Plus, I'll give you an even better structure than the incidence matrix for the system that we are going to implement. We'll see you in 15 minutes.